Let's look into next topic, ionization energy. So ionization energy is defined as the amount of energy required to remove an electron from its outer shell. It is called ionization energy. So it is, briefly we talked about it in chapter 3 when we discussed about photoelectric effect. The Einstein performed this photoelectric effect to find the energy of the photon, where he said that if we project enough energy on a metal surface until we remove the electron from it, that electron carries that energy that it is given if it is in excess of the binding energy with its nucleus. There we calculated how much of that extra energy is used by an electron to travel in the form of kinetic energy. So ionization energy is basically talking about similar topic. So how much of energy it is going to be required to remove an electron from its outer shell from an atom. So again, for ionization energy, you can find the trends in the periodic table. Again, you need to remind yourself about the Z effective trends in a periodic table. Z effective is increasing from left to right and increasing from top to bottom. Left to right it increases, and it's always a little bit dangerous to talk about the order from top to bottom for Z effective, because you're adding more protons but also you're adding more shells, so it is never like, you know, for sure you can say that Z effective is increasing, but only thing you can say for sure is that Z effective is certainly increasing from left to right. Z effective do increases from top to bottom for periods, like hydrogen, helium, sodium, potassium, like that, but it's like never a constant number. So a little bit, we are always a little bit, you know, reserved about saying that as a certain, but across the period, you can say it for certain that it increases from left to right. Again, what it means for the atomic radius, the Z effective is increases, we said that from left to right, atomic radius decreases, right? So what it means for ionization energy, if Z effective is increasing, atomic radius is decreasing across the period, what it means for ionization energy is, we're talking about how much energy it is required to remove an electron from its outer shell, right? To remove an electron, you're basically trying to overcome the attractions of a nucleus positive charge with the negative charge of an electron. There is an attraction between negatively charged electron with its positively charged nucleus. There is going to be attraction because they were oppositely charged. If you are trying to break that attraction, you're going to apply some energy, which is an ionization energy. If all elements are not going to have similar atomic size and radius, so they are going to have different ionization energies. So based on how smaller or larger atomic radius is going to be, you can predict its ionization energies are going to be either smaller or larger. As a thumb rule is, if an element is going to have smaller atomic radius, it's going to have greater attraction between its proton and an electron, which means it is going to demand large energy to break that attraction. So smaller radius is going to need greater ionization energy to get removed an electron from its outer shell. Whereas if you have a larger atomic radius, and if you're planning to remove an electron from the outside of that valence electrons, so because it is a larger element with a larger atomic radius, you can predict certainly that there is going to be a smaller attraction between its nucleus and its valence electrons. If there is going to be a smaller attraction between its nucleus and the valence electrons, you don't need to apply a whole lot of energy to remove that electron. Okay. So here we have an example whereas sodium metal in its gaseous state, when a sufficient energy is applied, it loses an electron to form elemental ionic form of sodium, Na+. So to get this process done, sodium required ionization energy of 495.8 kilojoules per mole, which means to remove an electron from 1 mole of sodium neutral element, you need to apply 495.8 kilojoules of energy. Okay, so whenever you remove an electron from its whenever you remove an electron from an element for the very first time, you will call that as first ionization energy, which is what it said here, first ionization energy. Most of the times, first, and in general, most of the times first ionization energies require less energy than the remaining attempts to remove the electrons from the same element, because it is going to be in general harder to remove electrons from an element. So if you want to remove more electrons, you need to apply more energy. Here we're going to mainly talk about first ionization energy values. When we talk about ionization energy values, we mainly focus on first ionization energy values because it is a good indicator of comparing one element ionization value with another element ionization value. But if you talk about second ionization energy or third ionization energy, it's going to get a whole lot more complicated because you need to think about many other factors, not just its relationship of one element with another element in the periodic table. So almost like 90% of the time, even in this chapter, we are going to focus on just first ionization energy, which it is going to talk about how much of energy you need to apply on an atom to remove the electrons from its outer shell. So here, if you see this chart, you can see that from left to right, ionization energy is going to be increasing, which means we are going to need to apply a whole lot more energy as you go across the periodic table to remove an electron from its outer shell. Why? It is because we just said that just because Z effective is increasing from left to right, is increasing and the radius is decreasing, the attraction between nucleus and its outside electrons is larger. Increases from left to right, left to right, left to right, because fluorine is going to have larger attraction between its nucleus and outside valence electrons. It is going to need a whole lot more energy to remove an electron from its outside valence electrons than, for example, oxygen, because oxygen is a little bit more larger compared to fluorine. So the attraction is not as strong as in fluorine for oxygen compared to nitrogen, where the Z effective is smaller for nitrogen compared to oxygen and fluorine. So the size of radius is a little bit larger than oxygen to fluorine, because the size of the nitrogen atom is larger. The outside valence electron is finding much larger distance from its nitrogen. So with its weaker Z effective, but its longer distance to the central nucleus and its outside valence electrons, it has a less attraction capacity from its nucleus to electron, which makes it a little bit easier to remove an electron from its outer shell compared to oxygen and fluorine. So you can make the same case for across the period like this. But if we talk about from top to bottom here, from top to bottom, we are saying you need a less ionization energy to remove an electron, because we can still talk about the effective, but it is more reasonable to talk about the atomic radius of different period elements in a group as you go down, because as you go down for each element, you are having one more core shell here, one core shell, second core shell, third core shell, 4, 5, and 6. You are having more core shells, which means the distance from the nucleus is significantly getting larger and larger and larger, because there is a new shell is being introduced for each element. The distance from nucleus to that outside valence electrons is going to get larger each time significantly. Because it is going to get larger in size, the Z effective is going to be weaker on the outside electrons as you go from top to bottom in a periodic table, which makes it easier to remove an electron from a group if it is at the lower level than the higher level in a periodic table. So because it is easier to remove, you're going to apply lot less energy to remove an electron. One thing that throws our students here is numbers get smaller, but we are saying easier. So if you need to apply more ionization energy, which means that atom is either smaller or smaller in radius, or you can find them at the top of the periodic table compared to the rest of the elements. So in a group here, let me use a laser pointer. In the group here, group 1, look at these ionization energy values. Hydrogen has about 1300, but by lithium you only have about 500, and it is getting smaller and smaller and smaller. Because the size of the radius is increasing, you don't need to apply much larger energy to remove an electron. That's why the ionization energies are decreasing from top to bottom in a group, but ionization energies increases across the periodic table because the size of the radius gets smaller. I know it's a whole lot, but there is at least some common sense if you know how to use and exploit the strengths of the effective and atomic radius and combine it with ionization energy. So whenever you try to answer any question for ionization energy, first of all, I want you to correctly predict the trends in atomic radius, right? We said atomic radius trends are said like this. Increases, increases for radius. So, and correlate that atomic radius with the ionization energy, you are going to have much more easier time in answering this question instead of directly thinking about and trying to remember this data. I do not want you to remember any one of these fixed values for the ionization values. I just want you to know the trends, and I want you to know how to derive these trends from the atomic radius and how to derive atomic radius from the Z effective charges. So think logically rather than try to remember any one of these values. Remembering any one of these values are not going to be helpful to you to answer any of the questions here in this general chemistry class or even in the future. You just want to know trends based on its logical explanation of its subatomic particles and how they were arranged in electronic configurations in different shells. Okay, here this chart is basically showing that trends exist in a periodic table that you could see it. So what this chart is trying to show it is the in general, as the effective increases, ionization energy also increases from left to right. That's what we have been saying. So how do you read it is, let me separate them as a group so you will have easier time to see. That is group 1. And from that to here, you have group 2. So as the atomic number increasing from group 2, from lithium here, we are saying that ionization energy increases, so you can find lithium at the lower level and neon at the higher level, which means ionization energy is increasing, right? And this is for group 3. You can find the same trend. Here you can see that there are different elements starting with sodium, and they were considerably having greater ionization energies with one or two exceptions. Again, we don't really have to bother about those exceptions because we have some explanation for it, but not at the initial general chemistry class that you need to worry about a lot. Group 4, group 5, and group same group 1, group 2. Let me correct myself a little bit. Instead of me calling them as a group 1s, trick me a little bit, they were actually periods. 1, 2, 3, 4, 5, 6. Wait a minute, are they? No, actually I'm right, sorry. I can just add Z then. Yeah, group 1, group 2, group 3, group 4, group 5, and group 6, right? So ionization energies increases from a period from left to right. Here, just going into a little bit more detail, just to explain one or two things why there is a huge shift. Let's see this example that is showing if you have two different elements that are in two different periods in a group, same group but two different periods, you will have this different electronic configuration. Let's see if you have within a given shell, electrons with a higher value of Lr in energy that is easier to remove. Okay, this is what throws me off here. This should be 3a as well. So if we are talking about a similar example, we should be talking about same 3a because here we are talking about 3a. So it is a typo that it said 2a there. So if you have a group 3a element, and if you're trying to put electrons either in shell 3, either in the S or P, depending on where the electrons are going, you're going to predict how hard or easier to remove that electron is. So for example, this is saying that if your electronic configuration ends with 3s2, or if your electronic configuration ends with the 3s2, 3p1, which one of these electrons is easier to remove? If you remember, we said that s orbitals are always at lower in energy compared to p orbitals in the same shell. So which means s orbitals are always going to be much more closer to the nucleus in comparison to p orbitals. And if you talk about ionization energy, which is the breaking of these attractions between nucleus and the outside electron, obviously it is going to be harder to remove an electron which is from s orbital, which is going to have greater attraction between nucleus and the s orbital, than an electron from p orbital, which is not going to have as much great attraction as an s orbital of the same shell. So this is going to be easier to remove, which means it's going to have a low ionization energy. Let's see, what is an example that would be? Let me put up the periodic table again. Okay. We're saying shell 1, shell 2, shell 3. So we're saying if you have magnesium and aluminum, which one of these elements is going to have, is going to require more energy to remove an electron from its outer shell, okay? So here you have magnesium with the ending electron configuration of 3s2, and here you have aluminum with ending electronic configuration of 3s2, 3p1. So if you have an electron in the p orbital, it is going to be easier to remove than if you have an electron in s orbital. So which means magnesium is going to have a greater ionization energy because we just said it is harder to remove compared to aluminum, which is easier to remove. So less ionization energy. So sometimes these numbers might throw you off because you're saying if it is easier to remove, it needs less ionization energy. If it is harder to remove, you need more ionization energy. So think of as how much energy you need to input in, how much of force you need to input in from the memory of photoelectric effect. If there is a strong attraction between nucleus and its valence electrons, you need to apply more and more power. And here we are trying to specifically point an example where within a shell, if you have an electron in S and a P, which is going to be harder to remove. If you have electrons in S, because S is going to be smaller in size and much more closer to the nucleus, it's going to be hard to remove, which means you need to have more ionization energy to remove an electron from the S. So I'll just write what elements it is talking about. Magnesium here, aluminum there. And magnesium is going to have greater ionization energy than aluminum. Okay, let's see. So here another example. Let's say if you have a similar scenario where you need to, again, if we are going to talk about a comparison, we should be comparing between same groups. Sorry that there is a typo here again. Let's say here we are talking about same group, which is group 5A. And here we are saying that sometimes, especially for electronic configurations, symmetry matters. We want to distribute electrons until we have at least a half-filled orbital, because it is going to have greater stability. That's why chromium and copper are going to have uniquely different electronic configuration, because they will end up with the D5 and the D10 as their electronic configurations. So similar to that, so whenever you try to disturb symmetry, usually you will get some negative consequences from that experiment. So in the case of this example, here we're saying that, okay, you have completely filled, partially filled, but completely 5A orbital with the 3 electrons in it here, but you have 3 electrons plus 1 more electron. So which one is going to be easier to remove is obviously the electron that is already paired than an electron that is unpaired, but which would make the orbital empty, because making an orbital empty would make that element much more unstable, which means more reactive compared to removing an electron from a paired orbital shell, which does not make it as unstable as completely making it empty. So it is going to be easier to remove this electron compared to this electron, because it would lose its symmetry and also it would be empty, instead of removing electron from the paired orbital, which would only make it partially filled. Okay. Let's see what example it could be. I'm just curious. Group 5A. Let's find it. So group 1, okay, shell 1, shell 2, shell 3, shell 4, shell 5, the group 5A. So we have electronic configuration of one time completely filled 3 electrons, 1, 2, 3, 4, 5. Let's see if you have. Okay, we are talking about an example between antimony and tellurium. It would be harder to remove an electron from antimony, because antimony is going to have, I wish I can write on this. No, I cannot. Can I? No, I cannot. I need extra software to write on it. Antimony is going to have a 5p3 electronic configuration, whereas tellurium is going to have 5p4 electronic configuration. So with 5p3 electronic configuration, antimony has 3 electrons in each of the 3 orbitals to at least partially fill them. Tellurium has one more electron than antimony, which means it will start pairing them. So if you are trying to remove an electron, a paired electron would make less fuss about losing that electron compared to an unpaired electron but completely filled. So more examples. So before I talk about this, I just want to give a summary again. This is very important topic. In future also, I'm going to refer to this topic, ionization energy, several times. I want you to have a good understanding of it. In ionization energy, we are talking about energy required to remove an electron from its outermost valence shell. Okay, so the factors that affects the ionization energy, which means like how much of energy you need to apply to remove electron, the factors that affects that is the ionic radius. If you know the ionic radius trend, you could easily predict what is the ionization energy is going to be in terms of relationship with another element in the periodic table. I do not want you to remember the exact number. I just want you to predict the ionization energy of one element with relation to another element in the periodic table if they were in the same group or same row. Okay. In general, smaller the ionic radius, more difficult it is to remove the electrons from that smaller ionic radius containing element. So you need larger ionization energy. In general, larger the ionic radius, it is going to be more easier to remove the electron from that element because the distance from the valence electrons and nucleus is larger, so easier to knock off that electron. So there is going to be less ionization energy to remove the electron. Okay, and what we discussed so far is about first ionization energy, which I am mostly interested in testing you, but briefly, not whole lot. We are also going to talk about second ionization energy, but I'm not super excited about it because we only briefly talk about it and it makes things more complicated. The only reason we talk about is to show how hard it is to remove electrons from completely filled core electrons rather than valence electrons. Okay. So if you apply enough energy, obviously it is possible to remove electrons from a nucleus, right? If you apply more energy, obviously you can break all the interactions between its nucleus with its valence electrons or all the outside electrons present of that nucleus. So it is the example showing if you apply enough energy like 496 kilojoules per mole, you could remove first electron from sodium. Whereas if you want to remove one more electron from sodium, you need to apply almost 10 times of the energy that you applied in the first case, because once the sodium forms, it has 10 electrons in it with the similar electronic configuration of neon, which makes it more stable. It is not going to lose that extra electron anymore because it is more stable now with its completely filled core electrons of 1s2, 2s2, 2p6. Having 8 electrons in shell 2, it makes it more stable, so it is not going to lose that electron easily or without giving a fight. So sodium gave a fight a lot, so that we need to apply 4,562 kilojoules per mole instead of just 496 kilojoules mole for first ionization energy, which means removing first electron. So in general, you need to apply more energy as you want to remove the more electrons from an element. Okay, here is the list that shows how hard it is going to be if you want to remove more electrons from the same element once you remove the first electron. So the common trend is that you are going to apply more energy as you demand to remove more electrons. First, let's look at the trends in periodic table from across. We already know that from left to right in a periodic table, ionization energy increases. Here you can find that ionization energy is from top to bottom increasing until neon, starting with lithium from the same row. As you want to remove the second electron from the same row of these elements, as you can see, they are making a lot more fuss. They are fighting a lot, but these numbers are not consistent. You cannot have the same expectation that you're going to have the similar trends of the ionization energy values for the first ionization energy value to second ionization energy value. If you are going to predict the second ionization energy values for an element, Do not try to use the atomic radius trends a lot. It is a big no-no. Only way you can find the second ionization energy values is by writing the electronic configuration of that particular element and see if it left with more valence electrons. It is the only way you can find that. In general, it is a little bit more challenging to think about. Not that too hard. No topic is too hard, obviously, in the chemistry, if you put your mind to it, but in general, it is a little bit challenging topic. Because here you see, lithium need a lot more energy than beryllium, right? Lithium need about 7,000 kilojoules, whereas beryllium only need about 1,800 kilojoules. It's not increasing, it's even decreasing. So your traditional explanation of as the size gets larger, ionization energy gets smaller, as the size gets smaller, ionization energy increases is not going to work that you use for first ionization energy. So it is because lithium, first electronic configuration is helium 2s1. If you talk about ionization energy 1, it loses its first electron and turns into lithium plus by losing one electron. But if you ask to do more of it, its current electronic configuration is actually 1s2, which is equal to helium. So it doesn't want to lose any electron from core electrons. Losing electrons from core electrons is usually hard for any element, which would make it destabilized. So it's usually not favorable. Because it is not favorable and it's going to be unstable, it has to be applied more energy to convince that element to lose that core electron. Whereas for beryllium, okay, let me write beryllium here. Beryllium has 4 electrons and its electronic configuration is going to be helium 2s2, which means even after losing the first electron, it's still going to have one more valence electron. So it is still upset about losing that electron, but it's not as upset about lithium because it doesn't have to lose the core valence electrons, right? So you'll find the similar issue as you go from top to bottom. In general, second ionization energy values are a little bit, challenging to find. You need to write the electronic configuration of those elements and check if the element has to lose a core electron or a just valence electron. If it is just a valence electron, it would lose again with not much fight. But if it is going to have to lose a core electron, it is going to put up a lot fight, which means we are going to need to use lots of ionization energy to remove the second, third, or subsequent electrons. All right. I want you to answer this yourselves before I explain the answer for it. So the question is asking, would you expect sodium or magnesium to have the greater first ionization energy, and which should have the greater second ionization energy? Which means the question is asking where you're going to apply a lot more energy. When you compare sodium with magnesium, sodium is, okay, I hope that you answer this question before I explain the answer. When you try to answer for first ionization energy, first of all, I need you to predict its atomic radius. Which one of the element is going to be larger or smaller? My prediction is that magnesium is going to be smaller compared to sodium because magnesium is to the right of the sodium, which means any element that is right of the element is going to have greater Z effective in a period. So it is going to have greater Z effective, which means greater influence on the outside valence electrons, which shrinks the atom size smaller. So if it has smaller atomic radius than sodium, magnesium will have a much harder time to lose that electron because those electrons are closer to its valence shell, to its nucleus than the sodium. So magnesium should have a greater first ionization energy values. Whereas when it comes to second ionization energy values, once the sodium turns into Na plus and once magnesium turns into Mg plus, let's find their current electronic configurations. Na plus is equal to actually neon, which means it has just core electrons left, whereas magnesium is equal to neon and another shell electron, S1 electron. So which means it's going to be much more harder to remove an additional electron because they were core electrons compared to here where it is easier to remove because it is still a valence electron. If you need to take any notes of that, I'll just pause a second. Let me show you here. So magnesium should have a greater ionization energy values because if it's a smaller radius. In the case of first ionization energy values, when we talk about second ionization energy values, sodium should have greater ionization energy of second ionization energy value because it has to lose the core electrons in the magnesium. Losing core electrons is always disliked by any element because having a completely filled core electrons represents the electronic configuration of the noble gases, which means it is more stable to be like that. Okay. Next, we are going to talk about another topic, electron affinity. I'll take a water break and restart. Here, actually, I have one more example on the ionization energy topic that basically shows how to calculate the attraction between the nucleus of an element with its interaction with the outside valence electron. Here you could use this Coulomb's law equation to calculate the force, the attraction between two charged particles, which is the nucleus. You're going to use the Z effective as its current charge and the valence electron's charge. The electron has negative charge. Here we are going to calculate it for both carbon and nitrogen. To do that, you need to know the atomic radius of both carbon and nitrogen and their current Z effective charges. So I'm going to show you the solution in a bit. So the question is asking calculate the attraction that experienced by the valence electron of a nucleus for both carbon and nitrogen. See which one is going to have greater attraction compared to another. Here, carbon has a Z effect charge of 3.14, while nitrogen has the Z effective charge of 3.83. So we already know that there is a trend in ionization energies. We know that nitrogen should have greater ionization energy than carbon because nitrogen is placed to the right side of the carbon in the periodic table. So we know the answer by the trends in periodic table, but here we are trying to show it with a example. Here, if you calculate the force of attraction for both the carbon using its Z effective and the charge of the valence electron using its atomic radius, it's happened to be a negative 5.3 times 10 to the power of negative 4, whereas for nitrogen, because it has a greater Z effective charge and a smaller ionic radius, it is going to have the Z effective of 6.8 times 10 to the power of negative 4. So here basically showing that nitrogen has about little bit more larger force of attraction than the carbon because nitrogen has a greater Z effective charge, which makes it to have smaller ionic radius, which means it is going to give larger force of attraction to the outside valence electron. So it just shows that if you have a smaller, if you have a larger Z effective, that is going to lead to the smaller ionic radius, that is going to lead to the greater attraction between the nucleus and the valence electrons, which is going to lead to the higher ionization energy. See, all of these are connected. Ionization energy is connected to the atomic radius is connected to the atomic size. Atomic size is connected to the ionization energy values.